Hi, I'm Bob. Welcome to the tutorial on the exercises and applications for the textbook Econometric Analysis, the 8th edition by Professor William Greene. Today, we will solve the application at the end of Chapter 3, Least Squares Regression. It's about the partial regression. We will find answers using matrix algebra in Stata and compare the results with those using the regress command. Please download the dataset from the link below. We can place the data file in the current directory. In Stata, the use command loads the DTA file into memory. The describe command displays the variable's name, type, format, and other information. We use the browse command to see the data matrix. In part A, we will compute the least squares regression coefficients in the regression of y on x1. x1 is the explanatory variable matrix that contains a constant, education, experience, and ability. We first use the make matrix command mkmat to generate the matrix x1. Second, we create the column vector y. Similarly, we use the matrix list command to see the matrix and the vector. We will compute the OLS estimator using matrix algebra. The OLS estimator vector B equals the inverse of x1 prime times x1 times x1 prime times y. It is identical to the estimates using the regress command. In part B, we will compute the OLS coefficient estimates for the whole set of explanatory variables. We generate the explanatory variable matrix X that contains all explanatory variables. Then we compute the coefficient vector B using the matrix form expression. It is identical to those using the regress command. In part C, we regress each column of the matrix X2 on X1. X2 contains 3 family background variables: mother's education, father's education, and number of siblings. We regress each of them on the 3 individuals' own characteristics variables. We use the predict command to generate the residual variables, and then create the residual matrix X2 star that contains the 3 residuals. X2 star is a 15 by 3 matrix. To find the sample means of the residual variables, we use the summarize command. The sample means are very close to 0. The reason is that the residual in the regression of x2 on x1 is the part of x2 that the effects of x1 were partialed out or ruled out. The constant term is in x1. After partialing out the effect of the constant, the residual variables are in the deviation form from their sample means. In other words, the sample means of the residual variables are 0. In Part D, we will compute the R² by the matrix formula. We generate the matrix M0 by its definition. It contains the identity matrix, uppercase I, and the column vector of ones, lowercase I. M0 is the residual maker for the constant term. Then we calculate the regression sum of squares, SSR, and the total sum of squares, SST. Finally, the R² equals the ratio of the regression sum of squares to the total sum of squares. It is the same as the R² in the result window after using the regress command. If the constant term is omitted from the model, the formula for the R² is as follows. The variables are logged in the deviation form. It is much higher than the R² with a constant. We can find it using either the matrix algebra or the regress command with the no constant option. In Part E, we compute the adjusted R². The equation relating the adjusted R² and the usual R² is as follows. Using this equation, we can calculate the adjusted R² from the usual R². We can also read the adjusted R² in the result window. It is much lower than the usual R² because it is adjusted by the degrees of freedom ratio n-1 over n-k. As the sample size n is extremely small, 15 in this example, the number of explanatory variables k, 7 in this example, makes the degrees of freedom ratio much higher than 1. Therefore, the adjusted R² is much lower than the usual R². In Part F, we will compare the coefficient estimates from different models. The first model contains two sets of explanatory variables, x1 and x2. According to the Frisch-Wahl-Levels theorem, the OLS estimator B1 in the multiple regression equals the estimator in the simple regression of the transformed y on the transformed x1. The transformed variables have been parceled out the effect of x2. Using the residual maker m2, we can write b1 as a function of m2, x1, and y. Similarly, we write b2 in terms of m1, x2, and y. Please check out the videos on the residual maker and projection matrices in another course, 5-minute Econometrics. Returning to this question, we write the second model with x1 and x2 star as the two sets of explanatory variables. We write the expression for the OLS estimator B2 based on the Fries-Wahl-Lowell theorem. x2 double star is the residual in the regression of x2 star on x1. Since x2 star is the residual in the regression of x2 on x1, we can simplify it into m1 times x2. We use the properties of residual makers m1, symmetric and idempotent. So B2 is the same as in the first model. However, B1 in this model does not equal the one in the first model. x1 star is the residual in the regression of x1 on m1 x2. We know that m1 x2 is the residual in the regression of x2 on x1. The effect of x1 has been parceled out. In other words, x1 and m1 x2 are orthogonal. So when x1 is regressed on m1 x2, the residual is x1. Therefore, B1 can be expressed as follows. It is the same as in the regression of y on x1 alone. We can verify the results in Stata. Model 1 is the multiple regression on x1 and x2. Model 2 is the regression on x1 and x2 star. Model 3 is the regression on x1 alone. We find that the coefficients on x2 star in Model 2 are identical to the coefficients on x2 in Model 1. The coefficients on x1 in Model 2 are the same as those in Model 3 when x1 is the only explanatory variable matrix. I add Model 4, where we regress y on the residuals alone. By the Fries-Wahl-Lowell theorem, the coefficients on the residuals are the partial effects in the multiple regression. In other words, we can get the partial regression coefficients on x2 by regressing y on x2 star alone, because x2 star has parceled out or ruled out the effect of x1. Thank you very much for watching this video. See you soon in the next chapter. Goodbye. Thank you for watching this video and subscribing to my YouTube channel. See you next time.